Welcome to The Explainer. Today, we are digging into a fascinating new paper that suggests what we think of as deep learning might just be, well, an illusion, a flat shadow of a much more complex reality. We're going to talk about a new paradigm that could fundamentally change how we build and how we understand artificial intelligence.
So let's just kick things off with a big question. We have these unbelievably powerful large language models, right? They can write code, poetry, they can ace exams. But they have this secret weakness. They can't truly learn from new experiences after their training is done. It's almost like, are they stuck with some kind of digital amnesia?
And to really frame this problem, the paper draws this powerful analogy to a real neurological condition, anterograde amnesia. A person with this can remember their past perfectly, right? But they are completely unable to create new long-term memories. Every new experience just fades away. Sound a little familiar?
And here's where you really see the core of the problem. Your brain, my brain, we are marvels of continual learning. Through something called neuroplasticity, our brains physically change and adapt based on new information. An LLM, though, its knowledge is basically frozen in place once pre-training ends. Yeah, it can process new info in its context window, but it can't integrate it. It can't truly learn from it. And that is the heart of this whole amnesia problem.
You know, for years, the mental model for deep learning has been this: a simple, flat stack of layers. You feed data in the bottom, it gets processed layer by layer, and an answer pops out the top. More layers means more depth. But this paper argues that this view is, well, it's fundamentally incomplete. It's like looking at a 2D projection of a 3D reality.
So what's the alternative? Well, the paper introduces a concept they call the nested learning paradigm. And this isn't just some new architecture, it's a completely new way of looking inside the models we already have, and it reveals this hidden structure that we've just been missing this whole time.
Okay, let's dive into this because this is cool. Instead of a flat stack, nested learning sees a model as a hierarchy of processes, and each one is operating at a different speed. So, at level 1, the fastest level, you've got stuff like the attention mechanism, and it's constantly updating with every single token you feed it. Then, way down at level 3, the slowest, you have the core pre-trained parameters. Those only update during that massive initial training phase. And in between, there's a whole spectrum of other potential learning speeds.
So, the crucial point, the lens that reveals this whole nested structure, is this concept of update frequency. It's all about how often a model's components change. Once you start organizing a model by that, instead of by its physical layers, you unlock this entire new paradigm. It's a total shift in perspective.
Now this is where it gets really wild. This new perspective, it reveals a hidden secret about one of the most fundamental components in all of machine learning, the optimizer. We think of it as just a tool, but nested learning shows us it's so much more.
I mean, think about it. We use optimizers like Atom or SGD to update a model's weights. We see them as the engine and the model is the car. But what if I told you that the engine itself was also learning? What if it's its own little mini brain with its own memory and its own learning process?
Now, to understand this, we have to look at how the paper redefines some core concepts. Get this quote: memory is a neural update. So a memory isn't a file you store, it's the act of changing in response to data. And learning, that's just the process of making those changes, those memories, more effective over time. Okay, quick definition we're going to need for this next part: associative memory. It's just a system that learns to connect things. It maps a set of keys to a set of values. Kind of like how your brain connects the key, which is a person's face, to the value, which is their name. Simple as that. All right, prepare for your mind to be blown a little bit. Let's look at one of the simplest, most common optimizers out there, stochastic gradient descent with momentum. From the nested learning perspective, this is a two-level learning system. The outer, slower loop updates the model's main weights, but the inner, faster loop, that's the momentum term itself. It's acting as an associative memory, learning to compress the history of recent gradients to decide on the next best update. It's a learner within a learner.
I mean, just let that sink in for a second. This is the big aha moment of the paper. This nested complexity isn't something new we have to invent. It's been right under our noses the whole time, hidden inside the very tools we use to train our models. We just didn't have the right framework to see it.
So, if this hidden structure exists in our old tools, what happens when you design a new architecture based on this principle right from the ground up? Well, taking these incredible insights, the researchers did exactly that, and they call it HOPE.
Hope is designed to actually learn over time.
It has what's called a continuum memory system. So not just fast and slow memory, but a whole spectrum of learning speeds. And this is the wildest part. It's self-referential. The model actually learns and modifies its own update algorithm as it goes. It's an AI that is literally learning how to learn, and it's all inspired by the different frequencies of our own brainwaves.
So the key architectural difference is simple, but it's profound. A standard transformer, it really has two speeds, a fast memory in its attention mechanism and a single-speed slow memory in its MLP knowledge layers. Hope replaces that one slow layer with the continuum memory system, a whole chain of MLP layers, each one updating at a different frequency.
Okay, so the big question, does this radical new idea actually work? Well, let's look at the numbers. On a whole suite of tough common-sense reasoning tasks, the 1.3 billion parameter version of Hope achieves a top-tier average score. It outperforms strong modern architectures like RetNet and Transformer++, and it even inches past the very powerful Titans model.
And that number, 57.23, it's more than just a score on a chart. It's a proof of concept. It shows that building an AI based on this multi-speed nested learning idea isn't just a cool theory. It can deliver state-of-the-art performance out in the real world.
So let's zoom out and think about the big picture. Why does all of this matter? This isn't just about building a slightly better language model. No, this is about fundamentally rethinking the path forward for artificial intelligence.
So, if you're going to take anything away from this, here are the three big things. First, the models we build aren't flat. They have this hidden depth that's defined by update frequency. Second, the tools we use, like our optimizers, are actually learning modules in their own right. And third, and this is the most exciting part, this gives us a concrete roadmap to finally solve that amnesia problem and build an AI that can continually learn and adapt to the world.
And that leaves us with one final, absolutely tantalizing question. The principles of nested learning lead directly to architectures like Hope, which can modify their own learning rules. Is this the key? Is an AI that learns how to learn going to be the next great revolution in the quest for true intelligence?
The future is certainly going to be interesting, that's for sure. To keep breaking down the groundbreaking ideas that are shaping it, make sure you subscribe to The Explainer. Thanks for tuning in.